mass spec data has been there for decades now, right? So what was the breakthrough in that enabled you and your colleagues to identify these post-translational modifications?
Great question. So I think we are in a special time in history because there's a convergence of two macro trends. One is the rise of proteomics. So we've seen for the past couple of years that the robustness and high throughput abilities of mass spec based proteomics has been improving dramatically over the past few years. And as a result, the signal to noise ratio of whatever we are looking at is higher. But the second macro trend, which is not less important, is the computational resources we now have to analyze this complex data. So starting with cloud computing, that now allows us to move from working on one CPU to now working on the cloud and using thousands of CPUs, and combining, of course, AI, because now we have so much data generated from each sample that the only way to decipher that is to look at the entirety of the entire landscape of the modified proteins and unmodified, so the entire epiproteome, and analyzing it using the most advanced AI and machine learning
So
methods.
when you're looking at the variables here, so you have whatever 25,000, 30,000 proteins and 60 modifications for each of those. So you multiply that, and that's a pretty big number of variables.
Yeah, so it's not only multiplication; it's actually exponentially increasing because or many of the amino acids along the protein may undergo modification, right? So
Yeah,
the
so you
number
have
of
the combination
combinations
of
actually,
modification.
yeah, actually exponentially increased, and that's a great point because that was a big challenge in terms of statistical analysis because you have now so much more data points, and the risk of overfitting and undersampling is, or what used to be called the curse of dimensionality in machine learning. That's a real problem. So we have developed clever ways to overcome that. And yeah, great questions.